Everyone, welcome to this video. In this video, I want to discuss about the component, that is the component of microwave. You can see the syllabus of this portion, that is we already cover up the transmission line and waveguide of the microwave. There are mainly two waveguide, that was the rectangular waveguide and the circular waveguide, and in the rectangular waveguide there is transmission elective and transmission magnetic mode can be exist, whereas circular waveguide transmission elective, transmission magnetic, and transmitted electric and magnetic mode can be exist. And we discuss about the power transmitted in both the waveguide, and finally we learn about the microstrip lines, right, about its characteristic impedance, that all we already cover up this portion. Now we want to discuss about the component means the component connected with the uh, with the waveguide. When the microwave transmit from one point to another point, there are various kind of connector or component are arranged to transmit this microwave, right. So this component we want to discuss about this component. Okay, there are two type of component, mainly linear and non-linear, and these are these like that, that is the waveguide T, magic T, heavy ring, coupler, ferrites, Faraday's rotator, gyrator, circulator, isolator, terminator. These are all the components. Okay. Before that, we need to learn about this parameter, like that scattering matrix, S matrix, properties of scattering matrix, quality factor, Q value, cavity resonator. We need to learn about this parameter. In the next video, we want to discuss about the components. These are the linear and non-linear component we will be learn about in the next class, right. So in this class we want to discuss about this portion. Let's start. And this is the book that we actually follow up for this portion. And I just say that there is the two types of component present in microwave. One is linear and other is non-linear. Linear means there is no directional property. That means in each direction they are the same property. But in case of non-linear, is behave differently in different direction. If the direction will be changed, the property of this component will be changed. Like, right. So in this linear, you can say example cavity resonator T is hybrid ring, directional coupler, magic T. Okay, and the example of non-linear circulator, isolator, gyrator, term, etc. These are the example of non-linear component. Okay, so at first we can say what is the cavity. Cavity means there is a hole in this rectangular waveguide, or there is a hole in a circular waveguide. Okay, so the cavity means there is a hole in this waveguide. Resonator, what do you mean by resonator? Resonator is that if this is a rectangular waveguide, or you can take a circular waveguide, if the frequency matches, resonance means the input and output will be matches. There's like that, if the frequency matches and power transmitter will be the maximum throughout this waveguide, then this will be called a resonator. The resonator, in the rectangular there is two mode, transmitter electric mode and transmitter transverse magnetic mode, and in case of circular also transverse electric mode and transverse circular mode. And from the previous classes, the uh, component, that is the magnetic field and electric field component for this rectangular waveguide will be like that, here written here. The in case of rectangular waveguide, the magnetic field will be like that, and the electric field will be like that, and the corresponding separation equation in both case, transverse electric or transverse magnetic mode, will be like that. And for lossless dielectric, this C square will be omega square mu epsilon, and the corresponding resonant frequency, if you want to know about the resonant frequency for this rectangular waveguide, will be like that. Okay. In case of circular waveguide, for transverse electric mode, the magnetic field will be this, and this corresponding resonant frequency, this f of r is will be the resonant frequency. This is the resonant frequency, resonant frequency with the expression like that. And in case of transverse magnetic mode, the resonant frequency will be like that. In case of circular, so these are to the resonant frequency in case of transverse electric and transverse magnetic, whereas in case of rectangular both the transverse electric and transverse magnetic resonant frequency will be like that. Now comes into the Q factor, quality factor of a cavity resonator. Quality factor measures the frequency selectivity of a resonant or uh, anti-resonant circuit. That's mean when the wave are coming through or passes through the resonator, then the quality, that is the how many frequency are selected when this passes through this resonator, and this will be measured with this maximum energy stored by energy dissipated per cycle. Here 2 pi given as a dimension, match of the dimension. W is the maximum power stores and P is the average power loss. This is the expression of Q, quality factor. Okay, and this can be written in the another form, that is omega 0 by delta omega. Omega 0 is the resonant frequency and delta omega is the bandwidth. Delta omega is the bandwidth, or and omega 0 is the resonant frequency, and this will be maximum when delta omega will be 0. If this will be 0, omega 0 will be Q will be infinity. There is sharp change. Delta omega 0 means this will be very sharp. When this is delta omega is 2 omega 0, this will be the half, and this is the minimum value of the quality factor. So the maximum value of quality factor is infinity. Maximum value of quality factor is the infinity. So maximum means tends to infinity and minimum means Q tends to half, right? Q tends to half. Okay. For any LCR circuit, that is the in the electrical, there is a inductor, capacitor and resistor series LCR circuit. The frequency will be 1 by LC plus minus R square by 4L square, right? And if R equals to 0, then omega 0 equal to 1 by root over LC, that is resonant frequency. If we change this omega in terms of in form of omega 0, that is we just common out omega 0, so there will be omega 0 square, and this is the omega 0 L by R. This is nothing but the another form of the Q, quality factor form of the quality factor omega 0 L by R, another form of this quality factor, that is the omega 0 L by R in terms of inductor. This is another form. So if we put Q tends to infinity, if we put Q tends to infinity, so we need to sorry, if we put Q tends to infinity here, if Q tends to infinity, omega equals to omega 0, so we obtain this expression, that is at omega equal to omega 0, Q tends to infinity. And another form, that is if you take Q equals to half, if Q equals to half, then omega equal to 0 and 2 omega 0, there is two possibility, one is plus, one is minus. So Q equals to half, that means this 1 by 4 Q square will be 1, so this will be 2 or 1, right? So this is the minimum case, that is the Q will be the half. Okay, so the Q will be omega 0 half I square L, that is the power power energy stored in the inductor, and this is the power dissipated, right, through the resistor, the power dissipated, and this is the energy stored. So this is W and this is P. So you can see here, that is the omega 0 is 2 pi f0 W by P, 2 pi P by f0. So this can be written in the W equals to energy stored and P by f0 is the energy dissipated per cycle. Actually we derive this expression. Okay. Next, if you take a single terminated cavity resonator, then this volume will be pi r square L. If this the radius will be r, if the radius will be r, then this is the pi r square L, right? And the corresponding surface area will be like that. Then the quality factor of the cavity will be this. So in the magnetic energy this is, and this is the electrical energy. So the power power can be written as like that, where R is the surface resistivity. Surface resistivity is at the surface there is a absorption. Surface of this cavity resonator will be absorption, that is the surface resistivity. So if you put this expression of quality factor omega w by p, okay, then finally you will get this expression, that is the omega mu by rs volume by 2 into surface area. This is the another expression in case of this single window, single or single port cavity resonator. Okay, there is a point, that is the longitudinal field is higher than the normal component. This longitudinal field will be higher than this normal component. Now we need to prove this relation. This is an important relation, that 1 by QL equals to 1 by Q0 plus 1 by Q external. What do you mean by this? That is QL, when if this is a micro SS is connected with a single port cavity resonator. This is the cavity resonator, circular cavity resonator, and this is the microwave source. So these are connected. The quality factor for this cavity resonator when is connected with the outer source is QL. When it does not connect within the outer source, then Q0. So what is Q0? Q0 is quality factor is a isolated cavity, and QL is the quality factor when is connected with the outer source. Okay, and Q external is the quality factor of the external source. This is the equivalent electrical circuit of this arrangement. When this cavity connected with a microwave source, then they are equivalent electrical circuit is like that. That is this microwave source, this is source, there is a resistance and there is a inductance, and this is a transformer transform the microwave, and this is the equivalent LCR cavity, this is the equivalent LCR. So this is source portion, this is cavity portion, and this is coupling. When these are coupling, this is the coupling portion, transformer, like the transformer. So if you combined this, then you will be get NVS n square ZS. There is a coupling is 1 is to n, if there is 1 is to n, and L will be n square LS, and this is LCR. Okay, this is the combined effect of this electrical circuit. Now if you wants to find out the quality factor, you know the quality factor omega 0 L omega 0 L by R, right? Omega 0 L by R is the expression of the quality factor. So in that case you can find for Q0, that is the omega L by R. For Q0 there is only this portion, there is no external source portion, that is the omega 0 L by R, and QL when is connected this, so you need to take this region. So omega 0 L here, this one and that one, that why the total L is L plus n square LS, and total R here is 2R, this resistance and this resistance, that's why total resistance will be R plus n square LS. Now if we take this n square s is less than this portion, this can be neglected only when we can take this L. Since we can write here, since coupling is small hole, so n is very small, so L is very small, that's why n square ls can be neglected. Actually here ls is very small compared to L, ls is very small compared to L, that's why L plus n square ls can be written as L. Okay, so here we can written as L, and this is R plus n square ZS. Okay, so if you write this, if you take, sorry, if you take R as a common, so this will be Q0 and this is taken as K. N square ZS by R is taken as K. So you can write 1 by QL equal to 1 by Q0 plus 1 by K Q0. When K is 1, then this relation can be proved, where in QXT will be Q0 by K, the external quality factor, Q0 is the intrinsic quality factor, and QL is the loaded quality factor. So the external quality factor, intrinsic quality factor, and loaded quality factor related by the relation 1 by QL equal to 1 by Q0 plus 1 by Q external. Q is the quality factor. Quality factor. Okay. Quality factor of this cavity resonator. Here this quality coupling, that is the K, sorry, this K is actually quality coupling. This is can be three value, that is 1, less than 1 and greater than 1. When K equal to 1, the resonator is matched with generator. That means this is the resonator and this is the generator. When the frequency are matches, then K equals to 1. Okay, and then QL equal to half Q external equal to half Q 0. These are the K equals to 1. Overcoupling, when K is greater than 1, the cavity terminate are voltage maximum in the input line at the resonance. Okay, so the cavity terminal are at the maximum voltage in the input line at the resonance. When the resonance happening, the input line of the cavity terminal will be maximum. Then K greater than 1. If you put this maximum standing wave ratio rho, so you can find out the relation from this, that is the QL equals to this QL equal to Q0 by 1 plus K. So QL equal to Q0, 1 plus K is the rho. You will get this relation from that. And another that is K less than 1, that is the cavity terminal are voltage minimum and the input impedance is equal to the reciprocal of the standing wave ratio. So K will be 1 by rho. So if you put in this relation, K is the 1 by rho, that is K equals to 1 by rho, you will be get this relation rho by rho plus 1 Q0. This relation is coupling coefficient and standing wave ratio. So there is three case: K is less than 1, undercoupling, greater than 1, overcoupling, and equal to 1, critical coupling. This is the corresponding curve of this ratio, that is the standing wave ratio rho versus Q, and this is the critical, and this is the critical. This is the critical coupling. This is three are the coupling. Okay. Now comes into the parameter, that is the scattering parameter, or simply you can say this is as a S parameter. This is the S matrix or S parameter. Simply you can say this is S matrix or S parameter. Okay, there is maybe a single port, 2 port, 3 port, 4 port. This is there is a single port or the 2 port or the 3 port or the 4 port. So these are the scattering, sorry, these are the possible port are actually used in the in the component. Okay, so the characteristic and property of any multi-port component. Multi-port means port is more than one, that is 2, 3, 4. These are the multi-port. Multi-port is defined in the corresponding S matrix. This multi-port characteristics is can be obtained from the S matrix or the scattering parameter. Using scattering parameter, we can link up this port, multi-port, that is the more than one port, more than single port is the multi-port. Okay. In circuit theory, in any two terminal network can be represented by different parameter. When if two terminal or above the two terminal, you can interlink this terminal parameter by this parameters, that is the high bit parameter, admittance parameter, impedance parameter, ABCD parameter. There is 4 types of parameter actually used to describe two port or higher port, two or higher port uh, resonator or the component. Okay. First one is the H parameter, high bit parameter. These are connected with like that. If we take two port, then V1 and uh, V2, I1 and I2. So V1 and I2 is connected with I1 and V2, whereas admittance parameter I1, I2 is connected V1, V2, and the impedance reactance or impedance reactance parameter, or you can say this is actually impedance parameter. Impedance impedance parameter is like that, V1 V2 connected with I1 I2, and there is another fourth one. This is the fourth one, uh, that is the fourth one, AB CD parameter parameter. Okay, there is another, that is the ABCD parameter, that is connected V1 I1 with the V2 minus I2. Okay, this is a special case. Why this is called hybrid parameter? You can see here, that is H11 can be find out when V2 is 0, H11 is the V1 by I1, V1 by I1. So V1 by I1 means voltage by current, that is the resistance, this can be resistance. Okay, short circuit because the output is 0, that is the short circuit, and V1 by V2, that is the reverse voltage gain, reverse voltage gain, right. So this is I1 equals to 0, that means open circuit. If you wants to find H12, all right, H21 means H21 means I2 by I1, I2 by I1 when V2 equals to 0. V2 0 means short circuit, and I2 by I1 means current gain. This is the current gain. Okay, current gain. And another one, H22 can be written as I2 by V2, I2 by V2, I2 by V2 means the uh, uh, inverse of resistance, right. That is conductance. You can say this is con at I1 equals to 0. This is conductance, right. So you can see these four parameter H11, H12, H21, H22, four are the different resistance, conductance, current gain or reverse voltage. These four are the different, that's why this is called hybrid parameter. Whereas here you can see Y1 is the V I1 by V1, that is the admittance, Y12 is the I2, I1 by V2, that is also admittance. That means for these four parameter is admittance, that's why I call this is Y parameter or admittance parameter. Whereas Z is the V by I, that is the impedance or reactance. That's why that's why this is called the impedance parameter. Okay, and this is a special case ABCD parameter. This is also another type of hybrid parameter, and that's not like a hybrid parameter. This is a voltage by current, like that hybrid parameter. But this is a special name ABCD since the minus sign. Okay, so that's it. There is four types of parameter actually used. Okay, now in general case, if we take a two terminal port, this is a two terminal port, and there is four parameter we taken, that is A1 is the normalized incoming wave amplitude in port 1 in the port 1, this is the incoming. In port 2 this is incoming. In port 1 B1 is the outgoing, and B2 is the outgoing in port 2. This is four parameter taken. So B1 can be written as this, B1 can be written as in the A1 and in terms of A1 and A2, A1 from S1 to 1 and this is S1 to 2. That means B1 is some component taken from A1 to A1, some component of A1 incoming of N1 can be reflected and some component from A2. That's why S11 that means coming from 1 and S1 to 2 coming from 2, right? So B1 can be written as S11A1 and S12 this is coming from 2 to 1 and this is coming from 1 to 1. Similarly, B2 can be written as this is coming from 1 to 2 and this is coming from 2 to 2. So in the matrix form you can write B1 by B1 B2 S11 S12 S21 S22 A1 A2. This is in the matrix form or in the vector form you can say B vector B cap equal to S into an in the operator form. Okay, this S matrix is known as the scattering matrix for two port or the simply S matrix. This can be actually scattering matrix or the S matrix of two port. There is a two port, then this scattering matrix will be like that, right? Where you can define S11. What is the S11? That is the B11 by A1 when A2 equal to 0. That is the reflection coefficient for port 1. That is the reflection coefficient. S12 that is the transmission coefficient from 2 to 1, right? 2 to 1. Similarly, 2 1 is the transmission coefficient from 1 to 2 and S22 is the reflection coefficient of 2 to 2. This is the significance of this fourth term, that is S11, S12, S21, S22. These four term significance are like that. This is the reflection and transmission coefficient. Okay. In case of the N port, this was the two port case. In case of the N port, we can write this B1 in terms of this B2 like that, Bn equal like that. So in the matrix form you can write this this is in case of the n number of port of this cavity. There is a n number of port of this cavity, then this will be happen. Okay. Now there is a important things, that is the property of the scattering matrix. We need to know about the property of the scattering matrix or the S matrix. Okay, scattering matrix or the scattering parameter or the S matrix represent transportation and distribution of the microwave. You can see here this matrix represent actually reflection and transmission coefficient. So this is the transportation and distribution of the microwave power among all the branches of the component. So using this scattering parameter, you can say about the transmission or distribution of this microwave among the all ports. All ports, what part will be the reflected, what part will be the transmitted. You can get this information from this S parameter, right? Number two, exact or unique representation is only possible for the passive linear waveguide junction. In case of the passive linear waveguide junction, we can represent this S matrix. Otherwise, you can say the exact form of the S matrix. This is another property. Number three, any junction with n number of arms, that is port, is represented by a n by n matrix. You can see here there is a n number of port and the matrix will be n cross n. So there is representation of n cross n matrix with the n square element. This there are the n square element. N cross n matrix means there is n square of a element and this element will be vanishing, non-vanishing, real or complex maybe. Okay. Number 4, this is 1 2 3 and fourth. The fourth says the matrix which represent such a linear passive junction. In case of the passive junction, this is a symmetric in this form. That means this scattering matrix will be the symmetry. This scattering matrix will be the symmetry. Okay. So this this will be the symmetry. So actually here this scattering symmetric matrix scattering matrix or the S parameter will be the symmetric. This will be the proof here. If B1 can be written is like that, B2 can be written is like that, Bn can be written is like that. But in form of the another form, that is the B11, that's when comes from 1 to 1 S11, this is 1 to 2, then B1 2, but you can write B 2 1 also, and so on. Actually here we write this, yeah, B11 B1 is coming from 1 to 1, B111, that is S11, coming from 2 to 1, that is 2 to 1, S21, 3 to 1 3 1, and so on. So ideally reflection, if we put, that is the A1 equal to B1, A2 equal to B2, and so on, you can write in this form, that is B1 B2 B3 and Bn equals to S nn A1 S n sorry 2 2 3 4 nn and so on. So you can write this, finally you can write, that is the symmetry, that's been this matrix. Actually the matrix will be symmetric. B1 can be written as S11 S21 S31, that whereas here right is 1 2, right, S1 2 1 3 1 2 2, and this is the 2 to 1. Okay, this is the difference. So here you can write this matrix, that is S11 S21 S31 and so on, whereas the previous matrix was this previous matrix was that is the S11 S12 S13 S1n, whereas S21 S22 S2n and Sn1 Snn. Okay, this was the previous matrix, but now this matrix change into the this form. You can see here, these are the these are the transportable matrix, so that's why this is the symmetric matrix, that way S matrix is a symmetric. Next next point is the unity property, that means the sum of the product of all the elements with the complex conjugate of the element for the particular row or column is unity. Within a particular row or column, this property, this matrix product with its complex conjugate will be unity. Because power in will be extra A and power output will be this. Now power is fit into any one port, say only one port, there is no outer port, so the output from all the port, which means P in will be output of the all the ports, so this is will be equal to like that, so this total will be unity. Okay, so the product of, that's mean the input power comes through the output power, and this is the total output, so you can write this Ik into Ik star, that's mean the any component product with its complex conjugate then gives you a 1 summation is 1 unitary property, that is. Next one is the zero zero property, that is sum of the product of each element of any row or column with its complex conjugate of corresponding element any other row or column is 0. That's mean mathematically we can see, if you product this Ik into Ij or Ik into Jk, this with complex conjugate, this gives you 0, the total sum will be 0. Okay, product of this element with the another one, here the row is the same, I is the same, whereas here column is the same, the row will be the same here, and this is the column will be the same, then this product will be 0. And property of the phase shift, if you next property, this phase shift, if any port is provided with a change in phase, that is Bi Li, this is the change in phase, then all the matrix element involving the index I will be multiplied by this factor. So there is a phase shift, this is the phase shift, then this is the phase shift, then what happened, this exponential, this term is the phase shift term, will be multiplied to each matrix element, each matrix element will be multiplied, that means all the elements will be shifted out, phase shifted out with this phase shifter. Okay, and this is the actual circuit to find out this S matrix parameter, that is the port 1, A1 is the input, B1 is the output, A1 A2 input, and this is output, and this is the matrix element S11, S12, S21, S sorry 22, uh, and this is the impedance in output, and this is the impedance sorry voltage in the input. Okay, so this is actually network circuit, and this is the symmetry property actually, and this is your homework, you must do this, I think you can do this. Okay, so that's it. For any query you must inform me. Thank you.